Now, as you can see, the title of my presentation is Our Created Universe. We're primarily going to talk about stars, galaxies, and just a little bit about the Big Bang. Now, we'll start our discussion by contrasting two separate models. On the one hand, we have the Bible that tells us everything was created in 6 days about 6,000 years or so ago. Every object in the sky was created specifically to glorify its creator, as well as to provide us with things such as signs and seasons. On the other hand, the Big Bang model says that everything formed all by itself billions of years ago. Exactly how many billions varies depending on which week you ask, but we'll just say billions for now. Everything can be explained by current secular theories, and the creation model, the creation explanation, is neither useful nor even desirable. So we often find ourselves portrayed in a battle between faith and evidence, but this is a false battle, I believe. First of all, the Bible is the authoritative Word of God. It's sufficient to know the universe's history. The Bible tells us how the universe came about, and that's all we need to know. I mean, if the Creator tells us how He created it, then that should be sufficient for us. However, as I said, evolution is a stumbling block for many people. Therefore, we can be thankful that, as Chris quoted Matthew, where it says, "Love God with all your heart, soul, and mind," that God does allow us to love Him, does allow us to love Him with our minds as well. He has not created a universe that appears to have formed all by itself in contradiction to His Word. Now, that's not what you're being told necessarily in the media and other places, which is what we'll be talking about tonight. Tonight we're going to look at all the evidence that's out there. Well, we don't have time for all the evidence, but I am going to share quite a bit of evidence with you that you're not being told about. You read the media, the news magazines, even the television programs, if you're still watching television, which you shouldn't be, but anyway. We're told that the Big Bang explains it all. Well, there's a lot that we're not being told. That's the theme of my presentation tonight. You will hear me use the word evolution to describe the billions of years models and explanations. Of course, evolution, strictly speaking, would refer more to biological things, living things, not stars and galaxies. But since the evolutionary astronomers themselves use the word evolve when they talk about their models, I can use them too. So the question we're going to ask tonight is, does the universe really support evolutionary ideas? Or does all the evidence that we look at support a creationary model instead? Now, a logical place to start would be all the planets in our solar system. Seeing as we live on one, and we've studied it rather closely, and some of the other ones we've landed spacecraft on, and we know a little bit about them too. Unfortunately, we won't be talking about that tonight because we did that at last year's conference. Those of you who weren't at last year's conference, you should have been. Tonight we're going to talk about everything else other than the solar system. We're going to talk about our sun. That being a very important object to us. It is the source of our life. If it was to turn off tomorrow, we would all be dead in a very short period of time. And we'll talk about other stars as well. We'll treat the sun as a star and see how it came about and how they came about. We'll also talk about our galaxy. This object you see behind me here is a barred spiral galaxy. Very beautiful object, and happens to be one that scientists today believe looks like the one that we live in. I can't show you a photograph of the one we live in because we're inside of it, but I can show you, and we'll be showing you, lots of photographs of other ones that we're looking at from the outside. And the current thinking is that the Milky Way galaxy, where we call home, happens to look like this shape you see here. Not only our galaxy we'll be talking about, but we'll be talking about other galaxies as well. On a broader scale beyond that, we'll talk about the universe, and we'll learn a little bit of physics along the way, but don't worry, it'll be painless. I'm also going to be having a lot of quotes here. Apparently, if you just touch the thing, it goes to the next slide. That's good to know. I'll be quoting a lot of people here. Other than the Bible, every quote I'm using is from an evolutionist, committed to the theory of evolution, believing in the billions of years, rejecting creation entirely. So you're going to hear these people say some very damaging things about their models. Keep in mind, they believe them. I'm not trying to say these people believe in creation. The opposite is true. I'm using them as a hostile witness, so to speak, that they believe in the model, and they're going to admit some things which will surprise you. So we'll start by talking about our sun. Again, this is a very important object to us. It's the sustainer of life on our planet as we know it. And here's what we're being told about the sun. Here's, if my thing would cooperate. Oh, it shows up there, but not here. So we're told that the sun formed about 4.5 billion years ago from a large swirling cloud of gas and dust. It started as a big cloud, and then, as you can see, condensed down to the center. Most of the material, moved to the center and formed the central star, that being our sun. And the rest of the material on the outside became our planets in our solar system. Now, we found out last year that the planets actually don't match this model at all, but we're going to skip them for now and concentrate just on the sun. So we're told that we have this model that explains how the sun got there without any creation being necessary. But let's talk about what we're not being told about the things we see. First of all, the dotted line you see here going across represents the sun's equator. That would be, of course, the middle point of the sun. Now, that equator should line up with all the planets in the solar system. Because if we start out with that big swirling cloud that condensed down to a flat disk, and then it all contracts to the middle, not all, most contracts to the middle to form the sun, the spin of the sun should match the spin of that disk. So the equator of the sun should line up with the disk of the solar system. Now, of course, the solar system isn't really a disk, but all the planets line up roughly in a disk shape. So that's what I'm saying there. So the evolutionary model predicts that the sun's equator should line up with the solar system. As it turns out, it doesn't. Here's where it actually is. You saw it move just a little bit there. And let's see if I can go back. It's going to let me. So here's where it should be. And there's where it actually is. Now, that's not much of a tilt, is it? It's only about 7 degrees. However, that little tiny angle, that little tiny tilt creates a huge problem. Think of the scale of what we're talking about here. The sun's in the middle, and this enormous disk formed, supposedly, around it. Or I should say maybe simultaneously. For the sun to not line up with that disk removes one of the primary reasons that supposedly supports the disk idea in the first place. Let's look at the scale of that problem. When you say 7 degrees, I mean 7 degrees is a pretty small angle. And it is actually a small angle, and if, I'm going to use some modeling here, if my fist was the sun and the solar system was here, a 7-degree tilt is hardly even modelable, can I use that word, modelable, with my hand. But the further away the planets are, then the more severe that tilt becomes. Everybody see that? Now, the distance from our sun to Neptune is about 2.8 billion miles. When you extend a 7-degree angle out 2.8 billion miles, you wind up with a severe problem with where that angle lines up, and you're off by 344 million miles. So all the planets, again, they don't line up exactly, but they're pretty close. The planets are orbiting the sun in a disk that, at its farthest point anyway, is 344 million miles from where it should be. So you have a choice, if you want to accept the evolutionary model, either somebody moved all the planets or somebody pushed the sun over. And which of those two is the better explanation? I will leave you to decide. So that's the equatorial tilt problem. Our second problem that we'll be discussing is called angular momentum, and here's where we're going to learn some physics. And again, it's going to be painless, I promise. You can actually do this particular experiment at home. And actually, I think most of you, some of you, I'm sure, have this device that I'm going to use in front of you in your homes now. Now, probably most of you didn't know you had an astrophysics instrument in your house, right? Well, here it is. It doesn't have to be a yo-yo, of course, but something tied to a string will do. And most of us have as kids, probably did something similar to this. Let's see, that's probably dangerous to do it over my head. I'll try it. Well, maybe I won't. We'll go sideways. So what happens if I get a weight on a string spinning, and then I stick my finger out as I'm still spinning it? What did the weight do? It sped up. Why did it speed up? Because the string got smaller. Why should the string getting smaller affect the speed of the weight? Because angular momentum has to be conserved. Somebody has heard the official definition of this before. When you have an object spinning, as I just did, you have three items involved. You have the weight, I should say the mass of the weight on the end. You have the length that it's spinning, and you have the speed, right? Now, the mass didn't change during my experiment. Obviously, it stayed the same. The length, however, got smaller. Therefore, the speed had to increase because that extra energy had to go somewhere. Makes sense to everybody, right? I mean, we've all seen this done at one form or another. Well, it turns out this is a tremendous problem for the evolutionary model of our solar system. Remember that everything formed from that swirling cloud of gas and dust billions of years ago. Well, that swirling cloud was several billion miles wide. Actually, that'd be in radius, so even bigger than that. All that material rotating in this big disk, which supposedly slowly condensed down to form the sun, what is it going to do as it's spinning and getting closer? The length of the string is getting smaller, right? So what's that material going to do? It's going to spin faster. Well, it turns out that the sun should be rotating as a result of this material contracting by about 400 kilometers per second at its equator. And what we actually see is about 2 kilometers per second. And if people aren't familiar with kilometers, 2 kilometers per second is about 1.25 miles. So the sun's rotating about 1.25 miles per second on its edge, which is about 200 times less than what it should be according to the evolutionary model. So, I mean, we didn't do a complicated experiment here, right? This is pretty basic, and we see what happens when something is spinning and the length gets smaller. This is not a complicated physics problem here, but it's a tremendous issue, therefore, for the solar system. Here's a quote from an evolutionist. There's a fundamental and insuperable or unsolvable difficulty with the model as described. A striking characteristic of the solar system is that the planets with about 1/700th of the mass of the system in their orbital motion account for over 99% of its angular momentum. There seems to be no way in which an initially diffuse nebula, that nebula is the cloud and gas thing, could evolve so as to partition mass and angular momentum in that way. It turns out that the angular momentum problem is one of the most important hurdles to be negotiated by any plausible theory for the origin of the solar system. And I'm sorry for the jibber-jabber there, but I wanted to verify that yes, they do acknowledge that this is a problem. Now we can ask, how long has this problem been known? Is this a new problem? No, it's not. The problem of the outward transfer of angular momentum has been a vexing dilemma for models attempting to explain the origin of the solar system. This is the rock on which most theories for the formation of the solar system have foundered. Theories for the origin of the solar system have, in general, failed to deal with this fundamental question. Fundamental question. Like I said, it's not hard. I mean, we proved it with a yo-yo. And again, this isn't a new problem. It was first realized 200 years ago when the nebula model was first proposed. Actually, this problem was the reason the nebula model was initially thrown away, because there was no way to solve this problem. But all the other models that came up with were worse, so now the nebula model is back. It's the one in all the textbooks and the science programs. Yet, as these two gentlemen complain, during the 1970s, the solar nebula concept became established as a fundamental assumption of astronomy, notwithstanding that its 200-year-old problems had not been resolved. There's another problem that the sun provides for evolutionary models. It's called the early faint sun paradox. We know that the sun is burning by thermonuclear reactions. I mean, the sun is basically a big hot ball of gas with thermonuclear stuff going on inside, and it keeps us all warm. However, when scientists model what's going on inside of there, they see that over time, over billions of years anyway, the composition of the sun will change as it uses up hydrogen and changes its overall composition. As the composition changes, as the types of material that make it up change, then its temperature changes too. And again, this doesn't affect us because this only happens over billions of years. But if you do believe in billions of years, then it gets interesting, because if the sun is actually 4.6 billion years old, it should have brightened by nearly 40% during this time. Now, if you think about that, if it's getting brighter over time, that means earlier on it used to be dimmer, right? Well, according to the evolutionists, life arose 3.8 billion years ago. Back then, the sun would have been 25% dimmer. Turns out that would have severe implications for life on Earth. Among other things, the average temperature here would be about 30 degrees Fahrenheit, which is, of course, below the freezing point of water. This would make the Earth an ice planet. This would not be a good place to live, by the way. However, evolutionists believe that the average temperature on Earth hasn't changed. Well, that's an interesting conundrum there for them, isn't it? And of course, this isn't a problem if the sun is actually thousands of years old. So if you want to believe in the billions, you have to deal with this faint sun problem. That's not the only issue, though, that makes our sun an interesting study for creation and evolution. We hear a lot from the evolutionist side that our sun is just this mediocre, average ball of gas lost somewhere in the universe. Carl Sagan said this: "Who are we? What are we? We find that we live on an insignificant planet of a humdrum star, lost in a galaxy tucked in some forgotten corner of a universe in which there are far more galaxies than people." Carl liked to belittle our position in the universe, didn't he? Well, as we talked about in our last conference, the Earth is far from an insignificant planet. It actually is unique in a lot of different ways. But for today, we're going to focus on this humdrum star comment. Is our sun really just this humdrum, mediocre, average star? No, it's not. It's actually very unusual. Our sun is classified as a type G, of which there are only 9% of all stars in its classification. About 80% of stars are actually class M, which flare often, and I'll explain what that means in just a minute, and would kill us all from radiation. So we should be very thankful that our sun is not an average star, because we wouldn't be here to talk about it. Our sun is designed just for us. If it was too massive, it would be unstable, and I'll show you some examples of that in just a minute. If it wasn't massive enough, then the Earth would have to orbit too close in order to keep us warm enough, and we would probably be experiencing tidal locking, which means that the same side of the Earth would always face the sun as it went around, similar to what our moon does on the Earth today, that the moon always shows the Earth's the same side. Sometimes it's lit and sometimes it's dark, but it's always the same side facing us because it orbits us so closely. The same thing would happen if the Earth was orbiting more closely with the sun. Also, our sun's position in the galaxy is vital for life here. Its galactic orbit, its route around the Milky Way galaxy, if you will, is more nearly circular than about 80% of nearby stars. Also, most stars, at least that we can see, are actually in binary or multiple systems. A binary means there's two stars together, and multiple means there's more than two, meaning 3 or 4. And here's a nice little computer animation of what such a system would look like. You see there's a large star and a smaller companion star next to it, and the artist was nice enough to put the cute little planet there as we fly out. Well, in reality, that cute little planet would not be a place you'd want to live on because the temperature swings on it would be quite significant. Sometimes you'd have radiation from one star hitting you and sometimes two, so the temperature swings would be substantial. Our sun also turns out to be unusually quiet and gentle. One 30-year study just concluded recently studying the star's photosphere, our sun's photosphere, the outer layers of it, and found that it's basically constant in temperature, which we take for granted because we don't know anything else really. But when we study other stars, it gets interesting. New Scientist had an article that said sun-like stars normally produce a bright superflare about once a century, and we'll see some examples of that in just a minute. Why a superflare has not occurred in the sun in recorded history is unclear. I think a consensus is emerging that our sun is extraordinarily stable. So let's look at what life would be like if we did actually live on a quote-unquote average star. Here's a star that just went through a flare, and you see there's a large shell of superheated gas blowing off of this thing. Imagine if you were living on a planet close to this thing, you wouldn't be there to watch it, you'd be fried. Here's another one, sending off explosions in two different directions at once, which is interesting for other reasons. It's an interesting study on why the explosions have taken this pattern. But my point is, imagine being next to that star on a planet, and, well, again, you wouldn't live to see it. There's also the issue of how old is our sun. All the books will tell you 4.6 billion years, but that's really an assumption based on the assumed age of the solar system. For direct observational evidence, an evolutionist astronomer made an interesting admission. He says, I suspect that the sun is 4.5 billion years old. However, given some new and unexpected results to the contrary, and some time for some frantic recalculations and theoretical readjustment, I suspect that we could live with Bishop Ussher's value for the age of the Earth and Sun, which is about 6,000 years. I don't think that there's much in the way of observational evidence to conflict with that. Key phrase, observational evidence. There's lots of theories that say it's 4.5 billion years old, but how much actual evidence, how much data, how many facts? Well, it's an interesting admission on his part, isn't there? So here's a summary of what you're not being told about the sun. Evolution says it should be aligned with the plane of the ecliptic, that disc-like shape that all the planets orbit the sun in. But it turns out it isn't. Evolution says it should have almost all the angular momentum in the system, and it doesn't. It should have been faint early on, but obviously it wasn't. And it should be an average star, but thankfully it's not. The sun was designed just for us. Now we're going to set our sights out further in the universe, and we're going to look at galaxies. This is a picture of the Andromeda Galaxy. It would look better if it was darker in here, but oh well. A galaxy is a collection of stars in addition with some dust and gas. There's typically billions of stars in an average galaxy. Galaxies come in various sizes, but 100 billion or so is considered to be the average. You see in this one there's spiral arms coming out from the middle. That's why they call this particular kind spiral galaxies, like so. You'll see different shapes of galaxies as we go. So here's what we're told about galaxies. We're told that they started forming soon after the Big Bang, which would then make them billions of years old. But here's what you're not being told about galaxies. Turns out the Big Bang couldn't have formed them, and we'll talk in detail about this in just a moment. So-called young galaxies that we see far off in space that were supposedly formed right after the Big Bang contradict the Big Bang model anyway. And we're also discovering large-scale structures among galaxies that the Big Bang can't accommodate. Let's talk about each one of these. We'll start with the question of where do galaxies come from? Well, I just told you that supposedly, according to evolutionists, galaxies came from the Big Bang. So here's the Big Bang in a nutshell. In the beginning, there was nothing. And then it exploded. Now, we don't have time to discuss all the problems of the Big Bang tonight. That would take billions of years. Boom, boom. But maybe for a different lecture. For now, we'll just assume that the Big Bang happened the way they describe, and we'll go forward. Now, I'm going to introduce another basic physics principle, and that's energy can be neither created nor destroyed. You might have heard the famous equation E equals mc squared. The E in that equation represents energy, and the m represents mass. So they are equivalent. If you remember your algebra, oh, and I haven't told you what c is. C is the speed of light, which is a very large number. So a little bit of mass multiplied by a large number would then produce a large amount of energy. That means that small amount of stuff, physical stuff, equals a large amount of energy. And we can go back and forth. We can transform energy to matter and matter to energy. We can't create or destroy either one, and that's my point. I'll give you some examples. We can convert matter to energy in different ways. The most spectacular way we currently have is through nuclear reactions. And that is where a small amount of matter produces a big amount of energy. We can also go the other way, which a lot of people don't realize. It turns out that if you take little pieces of matter, subatomic particles, usually atoms or pieces of atoms, and get them spinning around and then collide them with each other, that more particles come out of the collision than went in. All the energy that you added to get these things zipping around in these huge colliders will actually go into forming new particles. And what I'm showing you here is a picture of a particle detector. Every little line you see on that thing, yeah, it shows up here. Every little line is the path of a particle that came out of one of these collisions. And my primary point again is that energy and matter can't be created or destroyed. We can convert back and forth, but we can't create either one. And here are some examples. Number one, we need to eat food. If you stop taking in mass from which your body will make energy, you will eventually starve. You need to put gas in your car. Obviously, if you run out of gas, then your car stops going. Now, let's work this backwards for a minute. Where does the gas get its energy from? Well, it got it from the oil it was refined out of. Where'd the oil get it from? The oil got it from the plants and so on, perhaps animals, that decompose to make the oil. Where did they get it from? Well, the plants got it from the sun. The animals got it from the plants that they ate, which got it from the sun. So we can work it backwards and see how energy and matter were transformed and used each step along the way, but my point is, it's not being created anywhere along the way. In fact, if you ever go on a diet, you're relying on energy not being created. You're hoping that your body will be burning energy that you already have. You don't want your body to be just producing new energy out of nowhere because that would defeat the whole purpose, obviously. But the Big Bang, if you think about this, violates this principle in the largest way possible. I mean, your body cannot produce one single calorie of energy on its own. It has to get it from food. But the Big Bang says every calorie in the universe came out of nothing. Let's talk about some more basic physics here. If you get a cup of coffee and it's too hot and you put it on the counter and you walk away for 20 or 30 minutes, what happens to it? It gets cold. Why? Okay, the heat is transferred into the air. There's a transfer of energy. Why does that happen? What's driving it? Let me ask you this question. There's energy in the cup, obviously, right? Because that liquid is hot. Is there energy in the air around it? Yes, because we're assuming it's at room temperature, so there's a certain amount of energy in the room. Why doesn't the energy in the room go into the cup? Why doesn't the room get cold and the coffee get hotter? Diffusion, okay. Energy always flows from a higher concentration to a lower concentration. This is called the second law of thermodynamics. You've probably heard that if you've been in the creation movement for a while. This is one of its most basic manifestations. Energy always spreads itself out until it's even. Once the coffee reaches room temperature, as the coffee gets colder and the room gets a little bit hotter, once they reach the same level, they stop. And it never goes the other way. Energy never gets more differentiated, if I can use that word, right? When there's a difference between high energy here and low energy here, they always equal themselves out. They don't get worse. And we use this principle every single day in multiple ways. The lights and the computer and everything else in this room is operating by this principle. The power company, burning coal or whatnot, which again, are not creating energy, the power company is sending a voltage through the lines to this building, and we are relying on the high voltage versus the ground to send energy through our lights and our computer and so on to give us power rather. So energy always flows from higher concentration to lower concentration until they're even. Okay? I'll probably belabored the point a little bit there. But how could galaxies form in contradiction to this? The Big Bang was supposedly very, very smooth and uniform in its energy in the beginning. There were no large hot or cold spots to think of. The entire room was the same temperature, if I can use that analogy. Yet, we see galaxies, which 100 billion stars or so, very hot, surrounded by millions of miles of empty space, very cold. It used to be all the same temperature according to the Big Bang, but all the energy suddenly gathered itself together into these galaxies to make this spot hotter and all the surrounding spots colder. It's the equivalent of having a hot cup of coffee that pulls in more heat from the room, so you sit there with icicles dripping off your nose and it's boiling. I mean, we know this isn't the way the universe works, but this is how the Big Bang says it has to work. Does anybody see a problem here? There's also a problem as we look further and further out in space, in that according to the Big Bang theory, the further out we look, the younger, quote unquote, the galaxies should be getting. In other words, we're seeing galaxies that are closer and closer to how they looked back at the time of the Big Bang. The problem is, for the evolutionary model, that the galaxies aren't looking any younger like they expected them to be. This particular one here I'm showing you is not a young galaxy. It's very close to us. But this is an example of a spiral galaxy, which they hadn't expected to find a lot of as they looked earlier and earlier in the Big Bang. But they're finding these, which are quote-unquote mature, instead of the quote-unquote young ones that they had been expecting. We've looked back, supposedly, to 5% of the Big Bang age. As I just mentioned, there's lots of galaxies, which was a surprise. They're fully formed, and most were spirals instead of irregulars, which was also a surprise. They're also finding galactic clusters, not just galaxies, but clusters of galaxies spread out across the universe. Supposedly less than 3 billion years after the Big Bang happened. Well, they're not supposed to be there at that time. There's not enough time after the Big Bang for these things to have formed. Yet, there they are. And again, I don't accept the Big Bang or these billions of years ideas. I'm saying if you accept their assumptions, the data don't fit. Two prominent astronomers reviewed the 5 main competing theories of how galaxies got here. And their comment was this: we would not give very high odds that any of these theories is a useful approximation of how galaxies were actually formed. There's also what's called the lumpiness problem. Space is very lumpy. And doesn't that sentence sound ridiculous when it's taken out of context? Lumpiness, and what I'm talking about here, is that we have millions of miles of empty space, and then there's a bunch of stuff in one all together. And then there's more empty space, and then there's more stuff. For example, in our solar system, you have the Earth, and you have our sun, and there's 93 million miles of empty space in between, other than a handful of gas and dust and Mercury and Venus when they happen to be in between us. So there's planet, millions of miles of empty space, and then a sun. On a larger scale, the same thing is true. In between stars, there's millions of miles of empty space. And since we're talking about galaxies now, it happens on this scale as well. You have a galaxy, 100 billion stars all together. This is the Sombrero galaxy, which is even bigger than 100 billion, actually. And then empty space all around of it. But again, the Big Bang started out, everything was very smooth. You weren't supposed to have things clumping together like this. One of the most cherished notions astronomers hold about the structure of the universe is the notion that if we look at a large enough scale, we will find the universe to be smooth and homogeneous. From Einstein on, leading cosmologists have assumed this statement to be true. Here's what he's talking about. If one of us walked up to that wall over there, it's covered with fabric. If you had your face right along it, you would see the weave of the cloth, or maybe a painted wall, you'd see the lumps in the paint and so on, right? It would look lumpy to you, but when you get far enough back from it, it looks smooth. So the astronomers have applied the same logic to the universe. They say, well, we know, the universe does look pretty lumpy when we look at it, but if we stand far enough back, then it'll look smooth. And then it won't actually violate, it won't be lumpy anymore. And as I said, the Big Bang needs it to be smooth. Yet the fact of the matter is that the universe we know is lumpy. In our own neighborhood, it consists largely of empty space, interrupted by the sun and the planets and the bits of rock we call asteroids. Looking outward, we find a universe in which the visible mass is clumped into galaxies separated by large distances, the galaxies themselves being gathered into clusters. Try as we will, there seems to be no way to get a large enough view of creation to see a smooth, simple structure. Scientists find this state of affairs irritating. Now, why would a scientist find something irritating? Science is supposed to be about finding truth, right? Why would you find the facts irritating? The facts are supposed to be what you're looking for. Maybe because the facts don't match the evolutionary model that they want to be true. Maybe they're not fully objective in all this. Do you think that could be the case? Just how lumpy is everything anyway? This is one that probably doesn't show up hardly at all in a well-lit room. But this is a photograph from the Sloan Digital Sky Survey. The Earth is at the point of these two wedges here, and these cone structures are diagrams of galaxies that we see out as we look into space. Every dot here and here is a separate galaxy. You can see that there's filaments, that there's long strings of galaxies that go across the sky, and lots of voids in between. There's not only clusters of galaxies, the clusters themselves are grouped into superclusters, clusters of clusters. In between the clusters, there's what they call bubbles and voids. Bubbles, and because some of these clusters are appearing to be shells, and then there's a big bubble of space in between. Again, the Big Bang can't accommodate this. The Big Bang said everything started out smooth. You can't have energy just gathering itself together like this. So here's what you aren't being told about galaxies. Number one, the Big Bang can't have formed them. It violates conservation of energy, which is what we talked about first, and it violates the second law of thermodynamics, which we also talked about. We discovered that as we find younger and younger galaxies, they don't match the Big Bang model either, and clusters and superclusters of galaxies are making the universe very lumpy, while the Big Bang says it has to be smooth. It has always been difficult for astronomers to explain why stars are clumped into galaxies instead of being spread out more uniformly in space. There shouldn't be galaxies out there at all, and even if there are galaxies, they shouldn't be grouped together the way they are. The problem of explaining the existence of galaxies has proved to be one of the thorniest in cosmology. By all rights, they just shouldn't be there. Yet there they sit. It's hard to convey the depth of the frustration that this simple fact induces among scientists. Again, remember, everybody I'm quoting believes in evolution. They believe in the billions of years. They believe the whole thing. This is not a creationist speaking. A completely satisfactory theory of galaxy formation remains to be formulated. So we talked about our sun, and we talked about galaxies. Now let's look at stars. Where do stars come from? You would think that an evolutionary theory worth its salt would explain stars, right? I mean, stars are a pretty basic component of the universe. So if a theory can do anything, it should be able to explain stars. Now, why does evolution need to explain star formation in the first place? Well, it's because, according to our understanding of how stars burn, a star can't last for the 14 or so billion years that the universe has supposedly been around. For example, our sun is thought to be about 4.5 billion years old. It'll last another 5 or so before it goes through the next major stage of what it's going to do. And stars don't last for 15 billion years. A few only last for millions of years. So since evolutionists believe that the universe is 14 billion years old, and since we see lots of stars in the sky, therefore, we have to explain how stars are forming today. Now, if you follow the news, you will see frequent announcements of this new star birthplace that we just found. We saw stars being formed in this particular location. Here's one called the Cygnus Loop. You see big swirling clouds of gas and dust here, which I'll talk about more in a moment. Here's an example of what they called protoplanetary disks in the Orion Nebula. In other words, there's a sun surrounded by a big blobby disk of gas and dust where not only a star, but planets are forming, so they tell us. You might remember this one from a few years ago. This is a very famous picture of pillars in the Eagle Nebula. I'm going to zoom in on this part right here. And you see those little finger-like structures coming out. Supposedly, or so we're told, there are new stars being born at the tips of these fingers, these things sticking out from the cloud. So here's what we're being told. Number one, we know how stars are formed. And number two, we supposedly have even seen them being born. Here's what you're not being told, however. First of all, star formation supposedly occurs in the middle of a cloud in gas and dust, right? Now, these things are opaque. You can't see through them. Therefore, it would be impossible to see stars being formed inside one of these things, even if it was actually happening. What are the early stages in the formation of a star? What determines whether a cloud of star-forming matter will evolve into one, two, or several stars? Because clouds of gas, dust, and debris largely obscure all but the initial and final stages of the birth of a star, these questions have so far not been answered by direct observation. It has been impossible to date to view the cloud as it collapses through this range of densities. Consequently, stars cannot be observed as they form. No one has unambiguously observed material falling onto an embryonic star if the star is truly still forming. And no one has caught a molecular cloud in the act of collapsing. So where's all this evidence that we're being told about? Well, here's where they get it from. We can take pictures of clouds of gas and dust, nebulae, in wavelengths other than just visible light. We can take infrared pictures, we can take visible light pictures, we can take radio waves and X-ray pictures, all sorts of different frequencies. And in some cases, we can see things inside the dust that we couldn't see with just normal visible light. Here's an example of the Trifid Nebula. This is what it looks like through a telescope, a normal photograph. However, when you switch to infrared, you see how there's stars are forming there that you weren't able to see before. It's the same object, but there's superimposed different photographs taken at different frequencies. Does that make sense to everybody? So using infrared and other types of photographs, I'll use the word photograph even though it's not really it, we can see inside of one of these clouds. And we see, quote-unquote, stars being born. We see young embryonic stars. Well, how do we know they're young and embryonic? Well, scientists have worked out an evolutionary sequence for stars. They think that a star is born, it looks like this, and then it looks like this in this stage of its life, and then toward the end it gets bigger and turns into a red giant and looks like this, and then it dies. And so they have this nice little sequence. There's actually a multi-branch sequence. There's more than just one. But they believe they have a good idea of how a star will change over billions of years. Well, have we been watching stars for billions of years? No, obviously not. We've only been looking for a couple hundred with any degree of ability to see anything, and that's too slow of a time to see any of these changes occur. So how do we know this evolutionary sequence is accurate? Because, as I just said, the sequence would take billions of years to progress. So how do we know that this sequence is actually happening? Well, we see young stars forming in dust clouds, or so we're told. Proof is that we know they're young because of this evolutionary sequence, and so their youth confirms the evolutionary predictions that we see them in the dust clouds. What's the actual data that we're seeing? Well, we're seeing stars in dust clouds. I mean, that's the facts. So can an assumption confirm itself? Can you assume that it's young because of your sequence and the fact that you find it where you expect it to be proves it? I probably didn't say that very well. Does everybody get my point here? They assume an evolutionary sequence, and then they say we find confirmation of it. But in reality, we see stars in dust clouds. Now, what does the Bible say about this? 1 Corinthians tells us that there's one glory of the sun, another glory of the moon, and another glory of the stars, for one star differs from another star in glory. Is it possible that God created a bunch of different stars that look different from each other? Well, he said he did. Now, I'm not denying that there's good explanations in physics that if a star is of a certain mass and a certain density and given a certain amount of time, if it's burning hydrogen at a certain rate, that it's going to run out of hydrogen after a while and something else is going to happen to it. I mean, that's based on physics that we understand. And that might actually be going on today. But it hasn't been going on for billions of years. God could well have created the stars in the different stages, even if this sequence is actually true. So how are stars formed? How does a gas cloud form a star? Well, it supposedly collapses into a star. As I mentioned, our sun is basically just a big hot ball of gas that has thermonuclear stuff going on inside of it. And it turns out that we see a lot of clouds out in space that have hydrogen and the other materials that the stars are made up of. So scientists said, hey, obviously the stars came from the clouds. Well, how do you get a star out of a cloud? Let's talk about what a gas is, first of all. A gas is just a state of matter where molecules are not connected to each other. So in this room, we're breathing air. Air is in gaseous form. There's molecules of nitrogen and oxygen and carbon dioxide and other things. They're not bonded to each other rigidly. If they were, they would be solid. So the things you're sitting on, the molecules are bound together rigidly. If they're disconnected and flowing around freely, it's a gas. And if they're in between, if they can like slide like this, then it's a liquid. So we have a gas cloud out in space. In order to make a star out of it, you have to pull all these molecules together, which aren't attached, they're all zipping around, and compact them into a star. You have to collect them into a small area. How does that happen? Well, they say gravity will attract the molecules together. And that's true. Gravity does actually have an impact here. Even though a molecule is not very big or heavy, science tells us that everything with physical mass will exert gravity. And if you have a cloud of gas molecules, they will pull on each other. However, you also have gas pressure, which will force the molecules to disperse. So, which of these two forces will win? One will get you a star, and one will get you nothing, because the cloud goes away. So let's do another astrophysics experiment. Now, before I do this, it's 9:30 at night, and I've been showing you pictures of the night sky. So can we all stand up just for a minute to wake up? 10-second stretch break. Okay, please be seated. Now, I actually had an ulterior motive in doing that. And while you were all standing here, I was doing something to everybody. I was pulling on you. Now, you probably didn't notice. And I wasn't doing it on purpose, but that's what I was doing. I'm made up of physical material, obviously. So are you. That means that there's a gravitational force in between everybody in this room, between me and all of you, and between everybody and each other. Now, how could I have reduced the gravitational force between me and this gentleman here in the front row? Well, that's one. Okay, first way would be to reduce my mass. I can go on a diet. And that might be a good idea anyway, but that's not for discussion tonight. If you reduce the mass, then gravitational force goes down. Another way I could have reduced the gravitational force between us would just have been to step back. Because gravity reduces the further away you are from something. Now, think about this. How strong is a gravitational force going to be between molecules in a gas cloud? How heavy is a molecule of hydrogen? Infinitesimally small. It's not zero, but it's not much above zero either. How much force is it going to exert on another molecule a million miles away in this cloud? Also, not zero, but pretty close to it. And gravity is inherently a weak force anyway. Think about what I just asked everybody to do. Each of you has the entire Earth pulling you down into your seat. And you were able to counteract it just by flexing your leg muscles. Your leg muscles are stronger than the entire Earth's gravitational field. Feeling pretty good about yourselves, right? So gravity is a very weak force. Oops, let me back up a minute. On the other hand, we have gas pressure, which is the counteracting force to gravity in that cloud. Now, what do I mean by that? Well, on my high-tech astrophysics experiment device number 2, I have a can of compressed air. And somebody's wondering, who would be dumb enough to spend money on a can of air? Right? Well, use this to clean computer keyboards. Now, when I press the nozzle, everybody hear that? What's happening? It's expressing air. Air is coming out. Why is air coming out? Pressure. If there's gas inside of here, we already said the molecules are unattached, and they're all zipping around. There's zillions of them, technical science term, zillions. And they're all bouncing on the inside of the can, right? When I open the nozzle, I'm creating an opening so that the ones inside can communicate with the ones outside. Now, since there's more of them in here than there is out here, the ones inside fighting to get out are stronger than the ones outside fighting to get in. And if I was to hold this nozzle down, it would keep expressing until it was equalized. Remember the cup of coffee cooling, right? We went from high energy to low until it all smoothed out. The same thing would happen here. If I held this open, it would equalize until the pressure in here went up ever so slightly, and the pressure in here went down to match the outside. Now, how many people were worried that when I pressed this nozzle, instead of the air coming out, all the air in the room would be sucked in and we'd all die from asphyxiation? It's a ridiculous idea, right? How much air would you have to pack into this thing in order for that to happen? I mean, it could theoretically happen. If you got enough in here, well, the can would explode. But setting that aside, you could actually pack gas dense enough to attract other gas. But you understand my point. Gravity is a weak force. Gas pressure is a much stronger force. So, in our cloud of gas in the universe, out there in space somewhere, is this cloud going to stay a cloud? Well, the obvious answer is no. The only reason I get higher pressure in here is because there's a can. Well, where's the can in space? There is no can. So a gas cloud in space will disperse. How do evolutionists solve this problem? 2 ways, cooling and compression. The trigger for all that follows is a supernova event. I'll tell you what a supernova is in just a minute, which injected heavy elements, much of it in the form of fine dust and grains, into a surrounding medium, et cetera, et cetera. Basically, they're saying a supernova injected dust and material into this cloud and cooled it off. The picture here, imagine you're boiling a pot of water, and it's just barely boiling, and you dump in 2 handfuls of rice. What happens to the water? It stops boiling because you cooled it down by dumping stuff in that pulled the heat out of the water. They say the same thing happened here. A supernova throws dust and grains into the cloud, cools it off, which reduces gas pressure, incidentally, and allows it to collapse. Method number 2 is that when the gas cloud starts to coalesce by shock waves from supernova explosions. Now, that's twice I've mentioned supernova, so let's look at some examples. Here's a nice little animation of how this is supposed to happen, by the way. The supernova explodes, the shock waves hit the cloud, it compresses it and cools it, and then the nice little stars start to form, and everybody lives happily ever after. Now, are supernovas real? Yes, they are. Here's a supernova that happened in this particular galaxy. This here used to be as bright as the other stars in here. Now, how many stars can you make out in here? Basically none, right? Because this thing is too far away. Yet that is visible even though it's actually that. A supernova explosion is an enormous violent event in space. The Crab Nebula is the remnant of a supernova that exploded in the year 1054. Chinese astronomers noticed it. It was visible in the daytime for a number of days. So was this one here, which happened in 1987. You see this little ring structure here. This was the same size as that star there before, and now as you see, it's a big shell. But what is a supernova? I've showed you pictures, but I haven't said what it is. Well, a supernova is what happens when a star reaches a certain stage in its fuel burning. This gentleman, actually the Cambridge Encyclopedia of Astronomy says, after many stages of nuclear burning, the star's core becomes unstable and implodes while the outer layers explode. There's a massive output of energy. A supernova often outshines the entire light output of its parent galaxy for a week or more, et cetera, et cetera. So a supernova happens when a star runs out of a certain amount of fuel. It burns hydrogen for a while, turns it into helium. When that process can no longer happen, then under certain circumstances you can get one of these violent explosions. But think about this. If we need supernovae to make stars, and supernovae are old stars, that means we need old stars to make new stars. But where did the old stars come from? Well, they came from supernovae too. Well, where did those come from? Does anybody see a problem here? right? For the children in the audience, there's the classic joke about the chicken and the egg. Which came first? It couldn't be the chicken because you need the egg to make the chicken, but it couldn't be the egg because you need the chicken to make the egg. So which came first? Of course, as creationists, we know that God created the chicken. So we don't have to see. Creation clears everything up, doesn't it? It gives us all the answers. Well, why do the evolutionists recognize this problem? The process by which an interstellar cloud is concentrated until it's held together gravitationally is not known. Literally hundreds of ideas on how stars were formed have been advanced in past decades. However, we are still far from any real solution. By the way, this is on page 405 of one of my astrophysics textbooks. You wade through 400 pages of equations, and then you get... The origin of stars represents one of the most fundamental unsolved problems of contemporary astrophysics. Nobody really understands how star formation proceeds. It's really remarkable. Did anybody read about this in Time Magazine last week, or Newsweek, or PBS, NPR, any of the media? No, I didn't think so. Me neither. So here's what you aren't being told about star formation. It requires gravity to pull the gas cloud together. This is a very weak effect. Gas pressure will disperse the clouds. Instead, this is a much stronger effect. Therefore, you need old stars to form new ones, but nobody can explain where the first ones came from. So if evolution can't explain stars, let's think about this. What else can it explain? Well, first of all, it can't explain our sun because our sun is a star. The most important one to us, as I said. So scratch that off a list of what evolution can explain. Our neighboring stars in the Milky Way galaxy. No, they shouldn't be there either. Globular clusters, from hundreds of thousands to millions of stars. Well, what are they? They're just collections of stars. So if the stars can't be there, the clusters can't be there either. Galaxies, 100 billion stars. Well, again, if the stars shouldn't be there, then the galaxies shouldn't be there. How much can't evolution explain? This is a photograph called the Hubble Ultra Deep Field. And basically they took the Hubble Space Telescope and pointed it at an empty part of the sky for 11 days. And they saw nothing in this part of the sky. That's why they pointed it there. They wanted to see what would happen. And to give you some perspective on what you're seeing here, imagine the tip of your finger from the first knuckle on up. Imagine a piece of paper the size of that part of your finger. So we're talking smaller than a postage stamp, right? Cut that piece of paper up into 50 little pieces of equal size. How big is each piece? I mean, now we're down to like this, right? Imagine holding up one of those little pieces of paper and holding it at arm's length as you look up at the night sky. How much of the night sky does that cover? Hardly any, right? That's this photograph that you're seeing right here. When they left, this is the equivalent of leaving the camera shutter open to get a long exposure picture. They did the same thing here. Like I said, 11 days worth of total exposure time. Everything you see in this picture is a galaxy, with the exception of this, and that, the things with the fraction stars. Everything else you see in this picture is a galaxy with 100 billion or so stars. Here's some close-ups. Again, every little blotch, every little dot is another galaxy. And evolution can't explain any of it. The Big Bang is bankrupt. On the other hand, as Christians, we can look at the sky and say, wow. The heavens do declare the glory of God. So how useful are these evolutionary theories that we're being told explain everything? There are so many uncertainties in this picture that at present we do not really have a theory of star formation. Thank you for the tax dollars, though. If stars did not exist, it would be easy to prove that this is what we expect. The universe we see when we look out to its furthest horizons contains 100 billion galaxies. Each of these galaxies contains another 100 billion stars. That's 10 to the 22 stars all told. 10 to the 22 means write a number 1 and write 22 zeros after it, and that number is how many stars there are in the universe. Give or take. I mean, nobody's counted them, but that's an approximation. The silent embarrassment of modern astrophysics is that we do not know how even a single one of these stars managed to form. There's no lack of ideas, of course. We just can't substantiate them. I like that phrase, silent embarrassment. It's true. It's very embarrassing, and they'd like to keep silent about it. The correct perspective would be this. When I consider your heavens, the work of your fingers, the moon and the stars which you have ordained, What is man that you are mindful of him? It's amazing that God, who created all of this, which we can't even begin to comprehend, would yet care about us enough to send his Son for us to redeem us and make us his own. And that is the end of my time. Thank you.